Hi, I am Rachit Gujarati and I am here to talk about graphene, spintronic and use of graphene in spintronic devices. Okay, so this would be the agenda for this presentation. Alright, graphene is a semi-metal with a small overlap between valence and its conduction band, so it has zero band gap. It is often known as zero band gap material. It is one of the unique things that you will find about graphene. It is a form of carbon consisting of a single layer of carbon atoms arranged in hexagonal lattice. It is like a sheet in which all atoms are arranged in hexagonal shape and all atoms are of carbon. It is regarded as the world's first 2D crystal and the thinnest ever material in the world. It was first discovered in 2004 by Gem and Novoselic. It is the strongest material ever tested. So you can imagine it is thin, but it is very strong. It can conduct heat and electricity. And it is obtained from carbon in the form of graphene. So the name is graphene. It is cost efficient, so you can use in many applications because it has very good properties. Let's now see the structure of graphene. Graphene is a crystalline allotrope of carbon with two-dimensional properties. Its carbon atoms are densely packed in a regular atomic scale hexagonal pattern. Each atom has 4 bonds, one sigma bond with each of its 3 neighbors and one pi bond that is oriented out of plane. The atoms are 1.42 angstrom apart. You can remember that the silicon has also atoms that are 1.42 angstrom apart. It is very thin but stable, and its stability is due to orbital hybridization of s, a p in x direction and p in y direction that constitute sigma bonds. This is responsible for the most of the notable electronic properties of graphene. Moreover, it can also self-repair holes in a sheets when exposed to a molecular containing carbon. Bombarded with a pure carbon, the atoms perfectly align into hexagons, completely filling the holes, so it has self-repair property. Here are some physical properties of graphene. It is the thinnest material possible with two-dimensional property. Density of a graphene is 0.77 mg per meter square. It is very strong and have a breaking strength of 42 Newton per meter. That is even more than steel. So you can imagine how strong it would be. It is surprising very elastic in nature along with the strength it has. It is also transparent with absorption rate of only 2.3%. Now let's see some electronic properties. Graphene is a zero gap semiconductor as said earlier, and its conduction and valence band meet at direct point. The direct point are 6 locations in momentum space on the edge of the brilliant zone divided into 2 non-equivalent sets of 3 points. There are some electronic properties which separate graphene from the other condensed material, and we will see that in the next slide. And here they are. Let's see one by one. Electronic spectrum. Electrons propagate through graphene's honeycomb lattice, effectively lose their mass producing quasi-particles that are described by a 2D analog of Dirac equation rather than the Schrödinger equation for the spin of half particles. Single atom wave propagation. Electron waves in a graphene propagate within a single atom layer, making them sensitive to the proximity of other materials such as high K dielectrics, superconductors and ferromagnetics. Electron mobility. Experiments have shown that the graphene has a remarkable electron mobility at room temperature. Electrical conductivity. Graphene sheets are said to have an electrical conductivity of 10 times more than that of a copper. Alright, so Now there are some optical properties of graphene. Graphene's band gap can be tuned from 0 to 0.25 electron volt by applying voltage to a dual gate bilayer graphene field effect transistor at room temperature. The optical response of graphene nanoribbons is tunable into the terahertz region by an applied magnetic field. And the other properties are graphene is most reactive form of carbon owing to a lateral availability of carbon atoms due to its 2D structure. It has the highest ratio of edgy carbon atoms in comparison to similar materials like carbon nanotubes. It burns at low temperature. Now let us look at applications. It can be used in FETs, optoelectronics, fuel cells, and Hall effect sensors. Moreover, the applications are not just limited to this. It can be used in spintronics, quantum dots, organic electronics. Now, let me explain you the applications. Graphene has a higher carrier mobility and low noise, allowing it to be used as chemical in a field effect transistor. Graphene strongly interacts with photons, with the potential for direct band gap creation. This is promising for the optoelectronic and nanophotonic devices. Graphene supercapacitor could serve as energy storage alternative to traditional electrolytic batteries. It has advantages of fast charging and longer battery span. Due to the extremely high electron mobility, graphene may be used for production of highly sensitive Hall effect sensors. Potential application of such sensors is connected with a DC current transformer for special application. Okay, so let's now talk about spintronics. Spintronics is also known as spin electronics. It's a study of an interesting spin of the electron and its associated magnetic moment, in addition to its fundamental electronic charge in solid-state devices. Spintronics fundamentally differs from traditional electronics in that, in addition to charged state, electron spins are exploited as a further degree of freedom with implications in efficiency of data storage and transfer. Applications using spins polarized electrical injection have shown threshold current reduction and controllable circularly polarized coherence light output. Examples include semiconductor lasers. Future applications may include a spin-based transistor having advantages over MOSFET devices, such as steeper sub-threshold slope. This way, size of MOSFET can be reduced and more transistor can be placed on a chip, which will help to keep the Moore's law alive. We know that nowadays, as the devices are becoming very small, there is a threat to the Moore's law that it would be exploited. So this way we can help to keep Moore's law alive. Okay, so now let me talk about on what spintronic is based on. In spintronic, spin of an electron is more important than charge on it. We all know that the charge on electron is negative, but in what direction it is spinning, that is of interest in spintronic. Spin can have one of the two states, spin up and spin down. These states can be considered as binary logic 1 or binary logic 0. So for example, if it is spinning on right hand side of a curve, then it can be considered positive and the other should be negative. In certain materials, spin orientation can be used as spintronics memory, as these do not change when the system is off. Hence, non-volatile memory can be created through it. Spin electronics is already established in one critical area of digital electronics, namely in data storage. Considering the magnetic orientation with on or off current stage in binary logic, and we have a system of 4 states with 2 magnetic orientation forming a quantum bit, or it is also known as qubit. This provided this proved higher data transfer speed. Electron spin provides an additional degree of freedom to store and manipulate information. The read heads of modern magnetic hard drives exploit the spin-related effects known as giant magnetoresistance, that is GMR, and tunnel magnetoresistance, that is TMR. In both the cases, the result is the magnetic field sensor that may be used to read data magnetically encoded on hard drive platters. We talked about spintronics. Now let us see why we should use them in memories. The memory made up of spintronics are also compared to non-volatile memories like flash, but also compared to the mainstream memories like DRAM and SRAM. So it has advantages of both. The memories has unlimited read and writes. It has very less space and less power. So it is very efficient. It also has switching time very less, which enables fast performance. It does not require any specialized semiconductor or metals to join with. So this is the future of memory. Spin transport in graphene. Graphene is a promising material for spintronics, given that its spin properties can not only be tailored but indeed defined by what R atoms and other 2D materials you combine with it, says a scientist named Fabian. Once the right materials are identified, and this is what we are investigating in a flagship, a path opens towards specific technological applications. So, graphene is a very promising material for spintronics. Let us see why graphene is used in spintronics. Graphene, an atomic monolayer of graphitic carbon, is a promising material for spintronic application, owing to its capacity for room temperature spin transport over a relatively long diffusion length of several micrometers. Graphene also has high electron mobility and a tunable charge carrier concentration. Inducing magnetic moments in graphene is of vital importance if the material is to be used in spintronic. This could be achieved through defects in a material hexagonal crystal structure or the influence of absorbed atoms on its surface. One method of magnetizing graphene is by hydrogen, in which the hydrogen atoms chemically absorb onto graphene layer in a reversible manner. This creates an imbalance in the crystal lattice, thereby inducing a magnetic moment. Maximizing spin lifetime of an electron is critical when it comes to the application of graphene spintronics. Spin transport in graphene will only prove useful if we can achieve spin lifetime of nanoseconds and higher. Two mechanisms have been proposed to explain experimental trends, and both of these mechanisms have their origins in metal and semiconductor spintronics, and they each rely on spin-orbit coupling. Spin-orbit coupling is the interaction of an electron's spin with its motion, which leads to the shift in a particle atomic energy levels as a result of the interaction between the spin and magnetic field. However, recent studies show that electron mobility is not limiting factor for the spin lifetime, and scattering and impurities are not primarily responsible for spin relaxation. Hence, determining the primary source of spin relaxation is an important challenge for research on graphene, and if we can identify it, this will raise spin lifetime in graphene towards the theoretical value. Graphene's ability to maintain the spin of an electron over a long distance has made it very useful in the field of spintronics. Spintronics provide an alternative way to solve the problems which arise due to the limitation of Moore's law. The spin of an electron has attracted renewed interest because it promises a wide variety of new devices that combine logic, storage, and sensor applications. However, there have been a lot of limitation in the use of graphene in spintronics, and there has been a lot of research for making it more efficient and usable in devices. The reality is that graphene in spintronics is a maturing field of applied science and engineering, which holds a lot of potential for the future electronics. Thank you.